Hey everyone, this video is to discuss the second part of acid-base reactions. In the part one video, we covered what happens when you react a hydrogen-containing acid with a hydroxide-containing base. This video is to deal with the broader definitions of acid and base and to start thinking about conjugate acids and conjugate bases. All right. So we're given here a reaction equation in which we have HCO3 minus reacting with a sulfite ion, and on the product side we end up with just a CO3 2 minus ion, and now we have an ion that some places is called bisulfite, or you can call it hydrogen sulfite, either way it's fine. But what is really going on here? That's what we want to focus in on. So if you'll notice, over here, there's a hydrogen on the CO2, and there is not a hydrogen on the SO3 2 minus. Whereas on the product side, there is no longer a hydrogen attached to CO3 2 minus, whereas now there is a hydrogen attached to what was the SO3 2 minus ion. Also notice that the charge here goes from -1 to -2 for the thing that lost an H, and it goes from -2 to -1. Remember, when we write that minus like that, we always know there's an understood one, to -1. And this requires us to kind of rethink how we've thought about acids and bases just a little bit. So the way we're going to think of them is we're going to use a broader definition of acid and base. So our definition up until now is known as the Arrhenius, and I always have to think about how to spell it, definition, which is the Arrhenius definition is that an acid is something that produces hydrogen ions in water, and a base is something that produces hydroxide ions in water. So basically, the Arrhenius definition is what we were using in part one of acid-base reactions. If you go back and watch that video, all the acids contained H+, all the bases contained OH-. Now we're going to go with a broader definition. This is known as the Bronsted-Lowry definition. And the Bronsted-Lowry definition of acid and bases says that an acid is something that donates an H+. In the language of Bronsted-Lowry, a lot of times we say it donates a proton. Remember that that's the same thing because hydrogen most 99% of hydrogen atoms only contain a proton and an electron. If it's a hydrogen ion, it's missing that electron, and it's just a proton left behind. So anytime you see H+ or proton, those are basically interchangeable, right? And then the thing that we're going to call a base under the Bronsted-Lowry picture is that a base is going to be something that receives an H+ or a proton. Okay? So if it's donating or giving up an H+, that's an acid. If it's receiving an H+, that's a base. Okay? So let's try to apply those two definitions up here, and I'm going to give us a little extra space here to work through that. All right. So notice that, as we said, the HCO3 minus has a hydrogen up on the left side, on the reactant side, but on the product it does not. So it has lost an H+ or donated an H+. So we're going to call that the acid. The thing that's left over after the acid has given up its H+ over here on the product side, we're going to call that the conjugate base. Okay. That's a term that we're kind of going to just let hang for now. We're going to use this term a lot in second semester general chemistry, oftentimes because this reaction is going to be running backwards, sort of. Anyway, we'll get to that. But for now, we're just going to use the term whatever was the acid after it's lost its hydrogen ion, as the CO3 2 minus has, the thing that it turns into is the conjugate base. we notice again that the SO3 2- has no hydrogen on the left, but on the right-hand side, it has gained a hydrogen. So that means it's received a hydrogen ion. So we're going to call SO3 2- the base in this reaction. And HSO3 1- is going to be the conjugate base. Okay? Notice that when you go from acid to conjugate base, the charge changes from -1 to -2. Why is that? Because it's lost that positively charged H+. It's not just a hydrogen atom that's transferred, it's a hydrogen ion. So the base goes from -2 to a -1 charge because it's picked up that H+. So it's picked up not only the H that we see out in front, but it's gone up in charge from -2 to -1. Okay? So there's a couple of ways that we can look at this. And what I'm going to do is I'm going to give you a couple of practice problems on this, and I'd like you to try to do these on your own paper. So after I give them to you, pause the video, work them on your own paper, and then I'm going to explain, then you can restart the video and listen to my explanation. So in the first one, I just want you to assign labels. So assign the acid, base, conjugate acid, conjugate acid, and conjugate base for a reaction, NH3 plus H2O yields NH4 plus OH minus. Okay. Then also do another practice problem in which I'm going to tell you, I'm going to give you the reactants of a reaction. I'm going to give you HCO3 2- is going to react with NH4 plus. And what I'm going to tell you is that HCO 2- in this reaction is going to behave as the base. So now what I want you to do is predict the products based on that one piece of information, that the HCO3 2- is going to behave as a Bronsted-Lowry base. All right, so pause the video, try to work this out on your own, and then restart the video, and you can listen to my answers. All right, I hope you've taken the time to consider the answers. So what we're going to do here is compare the NH3 to the NH4 plus. A lot of times when folks are starting at this, they want to look at both reactants and figure out which one's the acid base. You can't do that. You have to compare what is on the left-hand side to what it turns into, what it most looks like, and what it's turned into on the product side. And you can see that we've gone from 3 hydrogens to 4 hydrogens, and we've gone up in charge. So that means NH3 has received an H+. The thing that receives the H+ is always the base. And the thing that turns into is the conjugate acid. Now we look here and we see that H2O has 2 hydrogens, and over here we only have 1 hydrogen. That means that the H2O has lost a hydrogen. That makes this the acid, and it makes the OH minus the conjugate base. I'm out of room here, so I'm going to abbreviate conjugate. All right. So notice again that the charge also has changed. The ammonia on the left is 0. It goes up to +1, so that means it's picked up a positive charge. The water goes from 0 down to -1 because it's lost an H+ with its positive charge. All right, so now we look at this next two, practice problem number 2. And we're given that this is a base, all right? So we know that that means that H4 plus is going to be the acid. So we're going to have a hydrogen transferred over to a hydrogen plus transferred over. So the HCO3, oh, and you know what? This is a typo. Oh my goodness, guys. Goodness. This should be 1 minus. That thing that I just drew doesn't exist. Sorry about that. That probably changes your answers. That's okay. So just follow along. So the HCO3 is going to now be, oops, that's the eraser. I'm going to be H2CO3 now. And it's going to go from a -1 to a 0 charge because that's gone up in charge. You don't have to write the 0. It's understood. And then the acid is going to have lost a H plus. So it's going to go from plus to 0, and it's just going to be NH3. All right. So now we can go ahead and label these. This is the conjugate acid, and NH3 is the conjugate base. All right. All right. I hope that's a helpful introduction to a broader way, the Bronsted-Lowry way, to look at conjugate bases, or excuse me, to look at acids and bases, and then assigning conjugate acids and bases. Feel free to leave questions in the comments.